Okay, so Gediminas, so thank you very much. So, okay, he's not here, but I'm thanking him anyway. So for setting up this fantastic meeting. So I think we are all having a great time here. So today I will talk about a couple of work in progress. So hopefully you will find them online quite soon. And here, so we are trying to propose alternatives to engineer no-local interactions in ultra-cold atomic systems, so associated also with geometrical frustrations. So as you know, no-local interactions are very important in order to explore state of matter with broken translational symmetries, okay? So a pragmatic example can be, for example, supersolidity. So supersolidity recently observed in three different experiments. But the crucial thing there is that these experiments are working in continuous geometry. So the situation becomes much more challenging if one is interested in observing breaking of translational symmetries in lattice geometries, so in discrete geometries. So usually this extended Bose-Hubbard is a good description of these setups. So and this is exactly the term describing the effect of no-local interaction. And in order to break translational symmetry, you need to have that this term is quite strong and large at distances equal or even larger to the minima interparticle distance, namely equal or larger than the lattice spacing. And people started to try to achieve this state of matter, and we got these beautiful recent results in the group of Marcus Greiner in Harvard. So here they have erbium, so magnetic atoms. So magnetic atoms have strong dipolar momentum, so which means that really you can have this kind of term. So you can really have long-range interactions. And here they observe a transition from a superfluid to a dipolar quantum solids, a crystal, or if you want, a density wave. So we also heard yesterday, beautiful results obtained in a group of Christophe. So what he has is not an incompressible state, so it's not an insulator like this one, but still you can break translational symmetry in an out of equilibrium configuration. So I would also like to point out that as we derived last year, so for example, if you want to observe topological properties, so Haldane phase or topological quantum critical points or charge density waves, so totally equivalent to the one-dimensional version of this state of matter, so you can also use dysprosium atoms, so magnetic atoms with an even larger dipolar momentum, but you need to work with this very small lattice spacing, and this is not easy at all to be done in an experiment. So here I would like to propose alternative method to have this state of matter, but in earth alkaline atoms, so not magnetic atoms. And I would also like to show you that these proposals are able to automatically include the effect of geometrical frustration. So let me just remind you what geometrical frustration means. So you can have different magnetic coupling, interacting coupling, or kinetic couplings competing. And if you have geometrical frustration, you cannot satisfy simultaneously all these coupling in a Hamiltonian. So a very simple example. So supposing that you have a triangular plaquette. So for simplicity, let's consider this triangular plaquette in XY plane. So and then you have, for example, ferromagnetic coupling, okay? So there I can clearly have a spin pointing up, another spin pointing up, and again, another spin pointing up. So I can simultaneously satisfy these three magnetic coupling. Now, think if I now change this sign. So if I have antiferromagnetic coupling between these two sides, so of course I have to flip this spin here, and then I don't know the orientation of this additional spin, because if I have an up spin here, I cannot satisfy this constraint. If I have a down spin, I cannot satisfy this constraint. And in this way, I produce a quite large ground state degeneracy. Okay, so let's write down the simplest Hamiltonian describing this configuration, just an XY model. So with the crucial ingredient that, okay, this magnetic coupling has to be positive, so antiferromagnetic. So clearly, I can map spin 1/2 systems in terms of hardcore bosons. So exactly in this way. So, and what the crucial thing is that, okay, again, here I need to have a positive sign. And we know that in ultra-cold atomic system, this is not easy because the usual tunneling amplitude has a negative sign, so it's negative. So we need to find a way to change this sign, and people started to think about that. So in particular, we had results more than 10 years ago in the group of Klaus Sengstock, so where they have an effective triangular ladder or triangular lattice. So, and in order to change this sign, they performed some periodic driving, some Floquet engineering. The thing is that when you perform Floquet engineering, you can produce heating in your system, and sometimes, you know, this heating kills quantum fluctuations. So, which means that you basically end up in a more or less classical system. Okay. So another possibility, as we heard Monday in the talk of Eugene, so is that you can have Fermi-Hubbard implementation. So you have Fermi-Hubbard model in a triangular lattice, so you can send the on-site repulsion to very large values. So you end up with an effective antiferromagnetic isotropic Heisenberg model. But the thing is that in order to observe antiferromagnetic coupling, so strong antiferromagnetic coupling, you need to work at temperatures well below the spin exchange. And this is not easy at all. So it has been done, but this is certainly not easy. So here I'm going to propose you different approaches, okay? So the first proposal that we have is based on cesium atoms. So two internal states of cesium atoms with opposite polarization. So we want to trap these cesium atoms in a one-dimensional optical lattice at the anti-magic wavelength. So roughly speaking, what does it mean? So it means that if one internal state, this blue state, is trapped in the minima of this optical lattice, the other internal state is trapped in the maxima of this optical lattice. So this is basically, you end up with two shifted sublattices, the green and the blue. And now the lattice spacing, instead of being the usual lambda over 2, becomes lambda over 4. So I can reduce by a factor 2 the interparticle, the effective interparticle distance. Now, of course, I can have tunneling amplitude between two minima in the same sublattice, this J JG and JB. So of course, these two tunneling amplitudes are equal, no? Because by definition, the two sublattices have the same lattice depth. Of course, I can also have on-site interaction. So if you work, so this is what at least our friends experimentalists told us, that if you work at 60 Gauss, this UBB is more or less equal to UGG. So basically you have homogeneous on-site interaction. And then you can use laser-assisted tunneling in order to convert one internal state into the other one. So basically, if you have a blue particle here, you can convert this blue particle in a green particle here. And this basically gives rise to nearest neighbor tunneling amplitude, and you can tune the strength, and you can also tune the phase. And this is going to be quite important. But the crucial point is that, so this specific internal state of cesium have a very interesting scattering properties. So if you now consider the interaction between particles in two consecutive sites of different sublattices, so what you get is that this effective nearest neighbor repulsion can be very, very strong. And not also can be very, very strong, it can also strongly compete with the on-site interaction. This U is just UGG equal to UVB. So you can see that you can have competition. So, and you need to, to consider the effect of this nearest neighbor repulsion. Okay, now we want to see how to include in this description effective geometrical frustration. Okay, so okay, this is the figure that you've seen before. So this is the tunneling amplitude between in the same sublattice. So next nearest neighbor tunneling amplitude. This is nearest neighbor tunneling amplitude on site and nearest neighbor. Now, let's just rewrite some of these terms in this way, and crucially, let's just fix theta equal to pi. So this is very doable in an experiment, and if you do so, you see that this Hamiltonian and this effective lattice structure becomes much more familiar, I would say. So because you see that if you fix this, this theta equal to pi, you get that the nearest neighbor tunneling amplitude is basically staggered. And now if you consider what happens here, so consider a triangular plaquette. Now just simply you have to shift the green sublattice, and you have to consider this green sublattice as an upper leg, the blue sublattice as a lower leg. And then the nearest neighbor tunneling amplitude just describes this diagonal hopping. Now let's see what happens in a plaquette. Okay, here we have clearly positive tunneling amplitude. So positive tunneling amplitude, I put the positive here and I get ferromagnetic coupling. Same thing here, so positive J1, I get ferromagnetic coupling. But since I have a pi flux, the odd links, so the tunneling between odd links, have a minus sign. I have a minus sign, I put here, and I get an effective antiferromagnetic coupling. So which means that I really get effective geometrical frustration. Now, okay, apparently this is a nice implementation, but we want to observe some interesting many-body physics. So we want to propose to use this scheme to observe something interesting, okay? So this is just a small portion of the phase diagram that we obtained. So we did MPS calculations. So okay, we fix U to strong values, but not super strong. This is for U equal to 6 in unit of J1. So, and then we change the level of frustration and the strength of the nearest neighbor repulsion. So here we have a superfluid, okay, nothing special. But here we have two different spontaneously symmetry broken phases. So in particular, this one is a bond ordering wave, so which is a spontaneously symmetry broken state where you break broken inversion symmetry. Basically, you have an effective dimerization, and this is an insulator, and this is an ordered phase. On the other hand, so once you increase the strength of the nearest neighbor repulsion, you break translational symmetry, and you end up exactly in the same phase that, for example, people had with erbium. So this is 1D, not 2D, but where you have a perfect alternation between empty sites and singly occupied sites. So, and here, you know, okay, this is nice because we can propose this alternative method in order to observe this kind of crystals or density wave. But what we are really interested in is, you know, the nature of this phase transition. Because here, you know, Landau, Ginsburg, and Wilson told us that if you have a phase transition between two ordered spontaneous symmetry broken states with different symmetries, of course, this phase transition has to be discontinuous, has to be a first order phase transition where the gap basically never closes, but just displays a finite jump between two finite values. We want to see whether this criteria, this rule, is respected or not. So these are our MPS calculations. So here we're working in the thermodynamic limit, so we don't have a finite size effect. So, and we see, okay, first, so these two order parameter, basically they go to 0 in the same point. So this is okay, is expected. And I would say continuously. So if they go to 0 continuously, so this is not compatible with the presence of a second order, of a first order phase transition. But then you can see, okay, maybe here there is a small jump. So maybe this is a weakly first order phase transition. In order to rule out this first order phase transition, we do plot the correlation length. So because we know that the correlation length has to diverge unically at criticality. So when the gap closes. And these, you know, are results for the correlation length as a function of the bond dimension. So this is quite technical, but you can see that specifically at this point there is a cusp, and this cusp strongly depends by the bond dimension. So pointing in the direction that here the correlation length diverge. So you can see here that the correlation length is already quite large. Furthermore, we can extract the central charge. So the central charge here is equal to 1, which is a strict criteria in order to say that we have an emergent U1 symmetry and that we have a criticality at this point. And furthermore, we can plot the decay of the correlation functions capturing these two phases. And of course, if you have that the gap is finite, at least one of these two correlators has to decay exponentially. On the other hand, we do find that these correlators goes to 0 algebraically and exactly with the same critical exponent. So which means that this transition is second order. So, and once we have a second order phase transition between two spontaneous symmetry broken state, this is something that has been already discovered 20 years ago in this paper. So it means that, you know, quantum fluctuations, so if you are deep in a quantum regime, quantum fluctuations are the responsible for the appearance of a continuous second order phase transition. And it is also possible, so here we don't have yet a clear picture, but it is also possible that this critical point is able to support the presence of something very special like emergent gauge fields and fractional excitation. So This is something that we are trying to better understand, but in principle, with this setup, we can observe this, I would say very interesting physical effects. Okay, this is all what I wanted to say about this implementation. So now I would like to show you a different setup where we can also engineer local interactions. So here, really long-range interactions associated with geometrical frustration. So here we are interested. 5 minutes, yeah, sure. We are interested in the setup that Ian Spielman has in his lab. So in particular, we have a sample of ultra-cold bosons. And in particular, ultra-cold bosons, these bosons can be in different internal states. And we know, for example, we can couple this internal state through two-photon Raman lasers. And what we would like to see, what the scenario that we are interested in is the one where there is a detuning. So basically, the energy that bosons have to pay to be in the internal state 1, 2, 3, slightly out of resonance. So if you are in this setup, so we can write down, an Hamiltonian, which is basically this one. So this is just the intensity of the Raman laser, and this is the coupling between different internal states. So here I'm creating a boson in the internal state, for example, J+1, and I'm destroying a boson in the internal state J. So for example, this coupling here, and you have also a pairs phase. And this is the effect of the detuning. So nothing special, I would say. But then if you change the basis of this Hamiltonian, so in particular you use this base, which is the basis of the dressed state representation. So what you see is that this term becomes quite interesting, because now you see that this Raman coupling is actually describes the presence of n cosinusoidal potential, and this is the effective lattice depth. And now you can see that, for example, if you have three internal states, you have three different sublattices shifted by lambda over 6. So you can reduce the lattice spacing by quite relevant factor, and this is even more spectacular, I would say, for 5 internal states, where you have that the minima interparticle distance is lambda over 10. Furthermore, so another very nice thing, I would say, is that now if you change, again, you work in this basis and you change this and you translate in terms of this basis the detuning, you end up with this term, which basically describes tunneling amplitude between different sublattices. So basically you can control the tunneling amplitude simply by tuning the detuning of your system. And furthermore, you can see that the tunneling now is not limited to nearest neighbor sites. So there is L, so you can have long-range tunneling processes, and also you have this phase. And this phase can be quite important. So let's try to build up an Hamiltonian. So okay, this is for 5 internal states. So as I told you, we have tunneling amplitudes. So, and as you can see here, this is for 3 internal states. So we have that the nearest neighbor and the next nearest neighbor tunneling amplitude is negative. So you put them here and you get effective antiferromagnetic coupling. So you get effective geometrical frustration. So this is even more spectacular, for example, for 5 internal states, where you have 5 hopping amplitudes. And again, you can easily change the sign and engineer geometrical frustration. So of course, you need to now take into account the role of on-site interaction. Quite easy. And now it is very important to have a look to the overlap between Wannier functions in different lattice minima. Okay, so if you do so this is, for example, you are gonna see that the blue Wannier function has a quite strong overlap with the pink, with the red, with the green. So which means that we can really have long-range repulsion here. So, and this is just the term describing this long-range interaction, but I want to give you some number. So in particular, for 3 internal states, you see that the effective nearest neighbor repulsion is very strong, so stronger than the one that you can have that they had with erbium, for example. And for 5 internal states, you have an even stronger nearest neighbor repulsion, but you can also have next nearest neighbor repulsion quite relevant. So now let's try to have a look to some many-body physics that we can observe here. So this is for density 1/2. This is the phase diagram that we obtain as a function of two detunings. So okay, here we have a superfluid, again, not interesting. Here we have a density wave, totally equivalent to the density wave that I showed you before. So breaking of translational symmetry, so perfect alternation between empty and singly occupied sites. But when you increase the level of frustration, you can also have a chiral superfluid. So it's a gapless state with spontaneously generated currents between consecutive sides of the different sublattices. So this is something also quite interesting. And for example, if you can extend this setup to 2D, this chiral superfluid would represent somehow an example of topological superfluid. But then I also would like to show you what we have for filling 1/3. So for filling 1/3, so here what we have, if you look, for example, at this density profile, you are going to see that between two maxima, there are always two minima. So which means that we can probably have a density wave with a different periodicity. So with period 3 instead of period 2. But in order to be sure about that, so what we need to plot is the structure factor. So the structure factor is the main smoking gun that you need to calculate in order to probe the presence of breaking of the translational symmetry. And here you can see that we get two well-defined peaks. So symmetric with respect to pi, and at 2/3 pi, so exactly reflecting the total density that we have. And finally, in order to be sure whether we have a density wave or a supersolid, we just have to plot the decay of the single particle Green function. Here we clearly see that the single particle Green function decays exponentially to 0, so which means that we don't have any phase coherence. So this phase is an insulator, is an uncompressible phase, but with a different periodicity. So which basically demonstrate the fact that we can have very strong long-range order, well extended the usual nearest neighbor repulsion. And I think I'm already out of time, so let me just thank the people involved. So the anti-magic wavelength project has been done in collaboration with two brilliant PhD students at ICFO, so Niccolò Baldelli and Sergi, who is now a postdoc, and unfortunately he's leaving academia in 2 weeks. And we got a very important experimental support from Cesar in Hamburg and Monica in Munich. And the subwavelength lattice has been done in collaboration with Gediminas and Domantas and Jan Spielmann at NIST. And with this, I thank you for your attention.
Thank you, Luca. We have time for a couple of quick questions.
Thank you, Luca. So my quick question is there perhaps an interesting prospect of looking into the entropy of these geometrically frustrated states? Is there maybe some interesting stuff going on?
Entanglement?
Yeah.
With entanglement, maybe you can detect in a different way some phase transitions, okay? So of course you're gonna see in some cases some different behavior depending by the phases that you are looking at. Now, regarding the story of the confined quantum criticality, entanglement can be very important. So there are results in this direction, but mainly for two-dimensional systems. So, I would say that we need, so first, we need to be sure whether these are real deconfined quantum critical points. So we need to perform some more advanced theory analysis. But once we are sure about that, then of course entanglement can be very, very important. On the other hand, so detecting entanglement in an experiment, it's not that easy.
Thanks.
Thank you, Luca. You said that you have two phases that are Z2 symmetry broken that have a line between them. So do you expect to have an increased U1 symmetry at that line?
We have an emergent U1 symmetry.
So you will have a Goldstone mode and you...
This is the theory analysis that you are planning to do. Yeah.
I see. Okay, thanks.